Hello and welcome to another video. Today we are going to be doing two pretty interesting things in the world of LLMs and RAG, with the first one being the combination of vector search with some more traditional relational database queries. And what that's going to look like in our scenario today is that we are going to have three types of data in our database, with the first one being a list or a table of Fortune 100 large companies. And we're going to build a vector search for these companies to allow us to flexibly find companies who are semantically related to a field or industry or similar to other companies, so a very typical use case for vector search. But then we're going to combine this vector search into a more multi-step retrieval process using two other types of data in our database, which is going to be some news items first of all. So we have some recent news items for each of our Fortune 100 companies, as well as some thousands of rows of numerical sales data for all the companies. And this way we can build a RAG system that can flexibly answer all kinds of different questions, more rich questions from the users against our data, so that we can retrieve not only the companies, but also the related information related to those companies. And one of the key components in achieving something like this is going to be some form of query planning, which means that when we have a user request, for example, to find robotics companies in the state of California and last week's news for each of those companies, we need to be able to figure out somehow what queries need to be run with what filters and parameters. First, we need to find the companies with a filter for the state of California and a vector search for the robotics related companies. But then we also need to be able to run a separate query to fetch the relevant news with a date filter there to only get the last week's news from our news table. And so we're going to be building this kind of a query planning setup using language models, as well as a very interesting library called Instructor, which, as it turns out, is going to be very, very useful for this kind of a situation. Now, when we talk about combining vectors with SQL-like databases, some of you might already be thinking about something like Postgres, which does make this possible with the PG vector extension that adds support to Postgres for storing and querying vectors. And while of course you can just create a separate vector store like Pinecone and a separate SQL-like database, but usually when you have the choice between managing multiple different databases versus having it all in one place, less is typically going to be the nicer choice. And so for this reason, and having it all in one place, Postgres is something that a lot of people are using for this kind of a purpose. Now today, instead of Postgres, we're actually going to be using a product called Timescale. And Timescale is a hosted database offering, which is built on top of Postgres. And originally they built the product to add some enhancements on top of Postgres, especially better performance when dealing with large volumes of time series data and real-time data streams. But last year they also released their new vector product as part of the broader Timescale offering. And this again is aimed at improving on PG vector, such as adding a more performant vector search algorithm, as well as other optimizations. Now the people from Timescale were actually kind enough to reach out to me about sponsoring this video. So I've been very happy to get to talk to their team, but also work with the product. So if you like what you see in the video, I can highly recommend you check it out. But of course, if you also just prefer to use regular Postgres, that's still totally fine. Virtually everything you see in the video should still apply almost one-to-one, because all the familiar tools that you would be using to work with Postgres, like the Python libraries and drivers that we're going to be using, they work equally just the same with Postgres and Timescale. So it's really up to you. You can choose which one you want to use. Okay, so here in our notebook, we are just going to start with some very standard setup. And the first thing I'm going to show you is how you can also set up Timescale, how you can sign up to the service and start using it. Now, normally you can go to Timescale's website and sign up for a free 30-day trial. But for you guys, you can use this link, which will be also in the description, to actually get 90 days of a free trial instead, with just your full name. And it says here work email, but you can actually sign up with any kind of email. I've also just signed up with my regular Gmail. I have the account already, so I'm just gonna sign in. And I also have these databases or these services already created. But if you have just signed up and signed in, then you'll create the service here. And you'll have two options. First of all, the one on the left is going to be the standard dedicated option, where you have a certain amount of memory and compute in your database, and then you pay a flat fee based on that amount. while on the right you have this serverless option where the amount you pay is determined by the actual amount of memory and compute or transactions that you use. And now we're gonna go with the option on the left, mainly because here we have this automatic time-based partitioning. And this is related to some of those time series data optimizations in Timescale. And we are gonna be working with time series data, so we are gonna be using those. And that's why we'll go with this option. Then we aren't gonna use any sample data, we'll bring our own. You can choose the region where your database is hosted between Asia, Europe, and the Americas. Select the amount of compute and memory. Then you also have this tagging option where you can differentiate between your development and production database. Mainly it's to just help identifying or separating the two. I think there are also some minor differences in the prod tag related to high availability or disaster recovery. I'm not entirely sure. In any case, that's not going to be important for our use case today, so we're just going to stick with the development tag. You can also enable a replica for your database for higher availability, as well as this connection pooler option, which can be useful for situations where you have a lot of short-lived connections to your database. A connection pooler allows you to basically use a more long-lived reusable connection and therefore reduce the resource overhead there. But again, that's not going to be important, so we'll just not choose either of these. You can give a custom name to your service or not, and then we'll just create the service. And so after creating the service, then here we can see all the database credentials that we're going to need for connecting to the database, and these we are going to copy over to our environment variables. So the username, password, the service URL, the database name, and the port. Now I have already copied all of these variables into my sample.env file here. So all the timescale variables here. On top of that, you're also going to need an OpenAI API key. And then also this event registry API key. This is used for the news API where I'm fetching the company related news from. So if you wanted to replicate that step as well, then that's also something you're going to need to sign up for. I'm not going to show that because I have actually saved all the news data here under the data folder. So if you did want to replicate, rerun this notebook, then you could just use the stored data here instead of using the API. But just something to keep in mind. If you do want to use the news API, then you'll also need this API key. Okay, but that's our timescale all set up. And then we can load those environment variables and create the connection. And we're actually going to create two different types of connections here. One using the PsyCop G2 Python library, which is just a very standard and popular library for interacting with Postgres in general. And this is also fully compatible with Timescale. And this connection we are going to use for executing SQL queries against the database. On top of that, Timescale also has this separate library, Timescale Vector. And we are going to create a connection using this client as well. And this client we are going to use for doing more of the vector interactions. So creating the vector table in Timescale, as well as doing the vector searches. I think you can also do that with just plain SQL, but I think it's just going to be easier to use this client for that. So that's why we are creating these two separate connections for Timescale. And then also, of course, we are initializing our OpenAI client, which we are going to need for a couple of things. Now with all that set up, we can start loading data into our database. And we're going to start with the company data. And so what we are working with here is this Fortune 100 company table. And it just contains some very generic company data, revenue, profit, number of employees for these large companies. And most importantly, we have this description column here, which is a few paragraph description of the companies. And this is what we're going to use for creating the vectors for each company and also basing the vector search on that. So that's important. And so the way we're going to do this is that first of all, we're going to read this CSV file into a pandas data frame. We're going to do some very minor cleanup of the data. We're going to rename the columns to convert them all into lowercase, replace spaces with underscores, and then also normalize some values in the market cap column. Some of them have non-numerical values, which we're going to replace into 0, and then just get the data frame back. And now, like I said, for upserting the data into Timescale, we are using the Timescale Vector client from the Timescale Vector Python library. And this is where this second function comes in, after we have read our data into a data frame, then the timescale vector client expects the data to be in the following schema. And that schema consists of these 4 columns. First one being the ID, which is a universally unique identifier for each vector or each row. And the second one is a metadata column, which is a JSON value column. And this is where we're going to put all these other attributes of each company. And then the third column is going to be the text contents on which the embedding or the vector is going to be based on. So this would be our company description that I mentioned before. And then finally, the fourth column is going to be the vector or the embedding itself of the contents or the description. And so this function takes our data frame and converts it into this 4-column schema. And this is where we create a unique identifier for every company. So using this UID library, we are going to generate a deterministic hash for each company based on the name of the company, and do that over all the rows in our data frame. And then for the metadata, like I said, this column is going to be a JSON value column. So for this list, we're going to have a list of dictionaries with keys and values. And what the keys and values are going to be, they're going to be all the other columns in every data frame row, except description, because as mentioned, that's going to go into its own column. But for all the other properties, we are going to save them into this metadata dictionary for each row. And that's how we create our metadata list. And then for the content list, this is super simple. We're just converting the description column of our data frame into a list. And then also the embeddings, relatively simple. For every item in the content list, we are also going to create an equivalent list of the embeddings for all that content. And we have this helper function to get the embeddings using the OpenAI client for that. And then finally, after we have created these 4 lists out of our data frame, then we are just going to zip those into a collection of tuples, each representing our rows. And if you are unfamiliar with the way the zip function works, let's see if I can actually create an example here. Perfect. So yeah, given some number of lists, like these 2 here, then if we zip those lists, we're going to get this list of tuples, where each tuple is going to be a combination of these 2 lists. So combining 1 and 4, 2 and 5, 3 and 6. So in our case, we're just going to zip these 4 lists so that the first value of each tuple is going to be the UID, the second value is going to be the metadata, the third value is going to be the content, and the fourth value is going to be the embeddings. And then this format is something that we can easily pass into our timescale vector client for this upsert command. So after we get these records, this list of tuples from this function, then we can just upsert them directly into timescale. So hopefully that makes sense. Now I have already loaded the data into my database, so I'm not going to rerun this now. But after we get the data there, now we can start doing simple vector searches. And again, for this, we use the TSV client with the .search method. And so just given a certain text query, we can again use our get embeddings helper function to vectorize that query. And then we can just pass that vector query into the search method, set a limits. You can also set up some filters and other conditions that I'm going to show later on. But for this one, we're just going to verify that the data is there and it works properly with the embeddings. And so for this robotics query, we get Raytheon, IBM, Lockheed, Alphabet. So just some technology and aerospace defense companies. So it looks good to me. But that's still nothing very exciting. That's just basic vector search. So now we are going to move on to actually adding some more data into our database, namely the news data and the sales data relating to each company. And we're going to introduce a few new tools here. First of all, PG copy. It's another very common Python utility for working with Postgres, and in particular, it's good for working, doing like large scale, moving large volumes of data from or to Postgres. And we're going to use that for uploading our sales data into Timescale. Again, like this is a Postgres utility, but it's fully compatible with Timescale. And our dummy sales data here has quite a lot of rows, so just using insert statements here would take quite a long time. So that's why we are using a PG copy for that instead. And then event registry. And so this is the news API that we're using to get some news items for all of our companies in the data. And we're going to do this using these two functions here. One is just doing the API call to get the company news, return the news items as a list of dictionaries. And then the second part is going to take that list of dictionaries and just insert those into Timescale using some very standard SQL. And again, here the data isn't going to be so much that we need to use a PG copy necessarily. So a simple insert is just gonna suffice. And now for the sales data, as I showed before, that data comes from this CSV here. So again, we are going to read that into a data frame. And with that data frame, first of all, we are going to convert the date in the CSV into a better, more suitable date format. So it works with the Postgres data type of dates. We are then going to convert it again into a list of tuples using this data frame method to get the rows as tuples and just pack that into a list. And then we are going to initialize the copy manager from PG copy. And it's going to take these three arguments. First one is going to be the connection, which defines the PsyCop G2 connection to our database, which we have defined here in the setup stage. And then the second one is going to be the target table, which is going to be sales. That's what we'll call the table. And then for the last one, we also need to define the columns of the target table in this list. And then we can just use the copy manager to use the .copy method, pass the data, which is our list of tuples from the data frame. And then that's going to do the conversion in just a very, very short amount of time, even for 10,000 rows or something like that. Cool. So here in the next cell, we're basically just going to be running those functions that I just described before. We are going to be recreating the tables first for both news and sales. And then we're going to be converting those tables into hypertables. The hypertable is a concept specific to Timescale. And for the most part, they are just like regular Postgres data tables, with the main difference that the data in a hypertable is going to be automatically partitioned by the date, which just means that the data is going to be separated into these different buckets based on the date range. And then you're just going to query them as you would a regular table, but those queries are going to be a lot more efficient because of this partitioning. So we are doing that here with this create hypertable function, where we just define which table we want to convert into a hypertable. And importantly, because of course this just works for time series data, we also need to specify what is the date column that the partitioning is going to be based on. So we are doing that both for our sales and news tables. And then we're just going to fetch the news data from the API, upload it into Timescale, and also read our sales CSV into a pandas data frame and upload that data frame into Timescale as well. Now again, I've run these already for my database, so I'm not going to run them again here. But now we can just verify that the data has been uploaded correctly to the database, and more importantly, that the keys have been generated correctly, so that all our news items have a relationship to a company as well as all our sales data. So we're just going to run this simple SQL join query, where we're going to join the news with the company table, filtering for company being Walmart, and joining them on the company ID, which is our table key. And then because we are working with these time series hypertables, we are also going to add this date filter for the news publication date, so that it's in the last 14 days. And we're going to see if that's going to work correctly. And yeah, we get 3 news items for Walmart. And now that's still not very interesting. That's still just a standard SQL query. But now we are going to move into the actual combination of vector searches with relational queries. And so what we have here is we have some themes that we want to find relevant companies for, smartphones and design in this case. And we are just going to create a vector search out of those, run the vector search with the TSV client, almost like before, with the vector query passed here, limit of 3. So we are limiting the search to 3 companies, 3 result companies. But also here we are demonstrating the other filters that you can apply. So you can also have a bit more control over your vector search results. And so in this example, we are filtering by state, which is an attribute in our company metadata. So just filtering the state of California. You could have a list of filters like this. But basically these filters only allow for very simple equals filtering. So the state needs to equal California exactly. Whereas we have then this other option for predicates, which is a concept in timescale vector, which allows us to use more refined logic for filtering. For example, filtering numerical values. And so in this example, we are limiting our results using these predicates to select only companies that have the number of employees being greater than 100,000. And then for each company in our results, in our vector search results, we can get the company ID from that result, and then we can run this corresponding sales query to get the total number of sales where the company ID is the company ID that we found in the step 1. And so then running that query, we get something like Apple, Intel, Alphabet, alongside their, of course, fictional here, but their total sales numbers. Okay, but that's still just a pretty basic coverage of how you can interact with timescale and how you can combine these different types of queries. But now let's move to the really interesting part, which is putting all of this into the context of a RAG type application, where the user is just asking these questions in natural language. And of course, the key concern there is how can we figure out which queries need to be run? Because again, we aren't just doing a simple vector embedding of the user question, but we actually need to figure out, okay, do we need to find companies? Do we need to run some SQL to get news or sales or both? Do we need to apply some parameters, some filters like state equals California or news from last week? So now I'm going to show how we can achieve that using this wonderful library called Instructor, first of all. And Instructor is a key piece here because it allows us to get structured outputs from language models. And before I go into full depth about what exactly that means, let's actually start at the end here. There's a lot here to cover, and I'm gonna try and explain as much of it as possible. But just going to the very end first, and here. The basic idea is that given a user question like this, get me AI companies in California and last week's news related to them. We need to figure out what queries need to be run and also what order those queries should be run in if there are dependencies, because of course before we can search for news, we first need to find what companies are we searching for news about. And we can achieve this with this query planner function that I've defined up here, which is calling a language model with some specific instructions. And this is going to give us exactly that. It's going to give us a query plan consisting of queries. The first query being the company search with the keywords to use for the vector search. We just have AI here, which could be better. You could have more keywords there, but it'll do. And also the filter for the state being California. And this query has no dependencies because we can just search for these companies straight away. Query type, company. This is also going to be important later. And then the second query, this is our news query. And here we correctly have the date parameters as well for this query, which correspond to last week's news or previous 7 days with the min dates and the max dates. And this one has the dependency on the first query because, again, we need to first find the companies and then find the news. Okay, so how exactly does this magic work? Up here, we have defined the class, a Pydantic class for the query plan. I'm just gonna hide this for now. But this is our query plan Pydantic class, and it has a list of queries. And queries is another class that we have defined up here, each of which have an ID, parameters, as we saw, dependencies, and then also the query type. And the way this comes into the language model interaction is that we have an additional parameter here that you might not have seen before, which is a response model. And this response model comes from Instructor, and I'm going to talk about that in a second more. But basically, we are just specifying here what class the language model output should correspond to. What kind of structured, defined structure should the language model figure out how to give us? And in our case, this structure is the query plan. And so that given that we consider the user question, generate the correct query plan. We also have some instructions, considerations in the query planner prompt system message here, which is just some additional context about what the language model should know about the kinds of queries we are running, the kinds of parameters that should be identified, etc. And it's a very simple library to use, all because you just need to have your OpenAI clients as per usual, and then you can call the instructor.patch method to patch that client, add some features on top of functionality on top of that client. And this is really all you need to understand. This is how we get the response model parameter as something we can include in our OpenAI language model calls. Instructor also works with a bunch of other services like Together AI or Ollama, which either use or mimic OpenAI's SDK structure. So it's compatible with those as well. Okay, but that's about as much detail as I need to go into Instructor here. I think that's about all you need to understand. Instructor just allows you to get back pedantic classes back from your language model calls. So you aren't just working with strings of text, but you're actually working with these classes that have predetermined properties. And as we are gonna look into next, these classes can also have methods. So let's look in more detail here about the classes that we have defined here exactly. This is just enumerable for the different query types, so we can limit the query types that we get into these three options, and if we get something else from the language model, then it doesn't pass the validation. But then for the query itself, we have these properties, as I mentioned before, but also importantly, we have this class method here, which is run. And this method, for a given query, just runs the query. And here we have some interesting logic, which just determines how the query should be run depending on the type of the query, because as we mentioned and saw before, all these queries are somewhat different. For the company search, we are using the TSV client's vector search, so that's what we are defining here. If the query type is company, then we run the vector search as seen before for the keywords that the language has defined as the query parameters. Also the filters. If there are filters in the query parameters that the language model has defined, then we also use those, but that could also be none if there is no filters necessary for the user question. And then we just get back the company name and the ID for all of these results. And the ID in particular is going to be important because that's what we're going to need to pass to our other queries down the line, such as the sales search. So if the query type is sales, then the query is going to look like this. We're going to run this SQL query against our sales hypertable, just getting the total amount of sales from a given company. And then here we're going to handle any possible optional date parameters as part of this sales query. So if we have both a min date and a max date in our parameters as per what we get from the language model, then it's going to be a date range, and we're going to append this between filter to our base SQL query here. Alternatively, if we just have a min date in the parameters, then it's just going to be a greater than or equal filter. For example, all sales after January 1st this year. And conversely, if we just have a max date, then it's going to be this less than or equal filter. And if none of these parameters exist, then we're just going to run the base SQL query and nothing else. Of course, executing it and just returning all the results. And then finally, the news search. This is almost identical to the sales search, with the difference that, of course, we aren't getting the sum of news. We are just getting the title in this case. But we could also get the full body, the URL, other data from this search if we wanted to. And so then the fact that all our queries, which are included in our query plan, have this executable method to run the query, then we can also have this high-level method in the query plan itself called execute. And this is just gonna run all the queries in the query plan, taking into account the dependencies as well. Of course, here it's very simple. We only have one type of dependency, so it's not very sophisticated how we are handling the dependencies, but nonetheless, we are doing that here. And yeah, we're just running all the queries in the correct order and storing all the results in this results dictionary. And then that dictionary is what we return. And what that means, given that all our queries that the language model defines for us have this executable run method, and our query plan itself has this execute method. That means that when we get the plan from the query planner function, which by the way is basically just doing the OpenAI call and nothing really else here. This is the query planner. We are just defining the messages here, and then the plan is the client chat completion with the response model of query plan. And so given this query plan that we get back from this function, then we can actually just call .execute on that plan for all our results. And so what that's going to look like, in this case, we have the two queries. We have the company search for AI companies in California and the news for those. So we get Apple, Intel, Alphabet, and then we get news corresponding to Apple on the first results, a news corresponding to Intel on the second row, and Alphabet on the third row. So just to hammer this home a bit more, how flexible this approach is, if we added here, really pushing the limits of the query planning here a bit, let's also get the last month's sales for each company, generate a new query plan for this new, more complex question. And by the way, this model dump method is just a method of any Pydantic class that you can use to print out the JSON representation of the class. So that's all that this is doing to make the plan visible, allow us to see that everything is in fact being generated correctly, which it indeed is. We have our two queries just as before. We haven't changed anything here. But then we also have this new third query for sales. This one also has the dependency on the first query, and then we have these dates corresponding to the previous 30 days or last month's sales. And then we can execute that again, and now we not only get the companies and the news, but then we also get the sales for each company. And just to bring this all home, of course, we can now use this to also generate a final answer to the user question if we want to have a more assistant-like experience for the user. So all that's necessary here is just passing the question, passing the query results to a language model with this different prompt to just respond to a user's question based on the results of several queries. And as a side note, we are still using the same Instructor patched client for OpenAI, because although we have done the Instructor patching and added support for the response model argument, we still don't need to use it every time. We can still use it just for regular chat completions where we just want text instead of defining some Pydantic class here for the output. So that's also not a problem at all. So now we just have the same question as we had before. This is the original user question. Get me AI companies in California, last week's news, last month's sales. And then we also pass the results from all the queries, and we print out the answer that the LLM generates based on the query results. All right, so that really brings it home. Hopefully this has been useful in starting to think about how you can go beyond just the text document search in your RAG and start to build these kinds of multi-query, multi-step retrieval processes as part of your RAG system, combining text with numerical data and some real-time time series data as well. There's definitely a lot of stuff there, especially all the stuff with Instructor. If this is the first time you're hearing about the library, and maybe you even have less experience working with Pydantic and classes before, it can definitely be a little mind-bending. But I can only highly recommend you check the library out. It's a very simple to use library, and they have a lot of great examples in the documentation. And of course, all the code in this demo is going to be available in the repo that I'm going to link in the description alongside other references. And with that, thank you for sticking to the end of the video, and I hope to see you on the next one. Thanks.